Alright, so the last thing we saw is the internal direct product of normal subgroups in a group. So let us start with that notion. Let G be the internal direct product of these normal subgroups. We know what it means. It means that every element in G is expressible as a product of elements coming from these ni's. That is one condition, and the second condition is that any such representation is unique. That means for a given element of G, there exists only a unique choice of elements coming from the ni's such that their product in that order is equal to G. So existence of such a product and its uniqueness together give us this thing, that G is the internal direct product of these normal subgroups. One more thing, when we say internal direct product, it's automatically understood that the subgroups involved need to be normal. So there is actually no need to separately write normal subgroups, but I have simply written it so that we can remember that the subgroups are normal. Okay. Now we can also consider the external direct product. T of these ni's. Why? Because the ni's, after all, forgetting that they are all subgroups of G, we can treat them as groups in their own right, and that is why their external direct product can also be considered. We feel that this T and G are somehow related. In fact, today we are going to prove that these are isomorphic. In fact, as groups, T and G are the same thing. And once we prove this, we can get rid of that prefix internal and external and simply say direct product. So towards the proof, we are going to first prove an elementary lemma, and then that will be used in proving this result. So let us first see the lemma. This is lemma 2.13.1. 13 because it's the 13th section. Let G be the internal direct product of these subgroups. And here note that I haven't written normal subgroups. These are normal, that is understood from this sentence itself, that G is the internal direct product of them. Internal direct product is defined only for normal subgroups. Then for distinct suffix values I and j, where each of I and j of course is any integer lying between 1 and n, including 1 and n. If you take the intersection of ni and nj, that is trivial. This is the first claim, and there is another. Also, if A is any element in ni, and B is any element in nj, then they commute. Okay, so let us first prove this lemma. So we are first of all going to prove this, that the intersection is trivial. Let x be any element in this intersection. Now we are going to write x as a product of elements of these ni's, of the n's, in two possibly different ways. And then we are going to invoke uniqueness of such products to claim that the two products are actually equal, and that is going to give us something. Note that we can write x like this. Oh, but before we write this though, I think one more assumption will be needed. Since it's not there in the book, but it's necessary to write this. Since I is not equal to j, we can assume without loss of generality that I is less than j. One of them will be less than the other, so we have simply assumed that I is less than j. Now note that x can be written like this: E1, etc., E2, E3, and so on, ei minus 1, x e I plus 1, ej en. Now we need to say what these e's are. These e's are actually nothing but the identity element, where et is equal to e, the identity element in G. However, we are writing them with suffixes. That's because we want to treat these as identity elements in the ni's. For example, E1, although it's simply E, is the identity element in N1. The next one, E2, is the identity element in N2. We are using the suffixes so that we can show how we have written x as a product of elements of these n's. So this E1 is interpreted as coming from N1, E2 is coming from N2, and so on. Ei minus 1 is coming from N suffix I minus 1. What about this x? You can think of x as coming from Ni. That's because x actually is in Ni. And then the next element we have chosen as the identity, and so on. It goes like that. So all of these e's are actually nothing but e. And x belongs to Ni, which means that this is a product of elements of these n's in that order. And that turns out to be nothing but x, because after all it's just one x and all of the others equal to the identity e. Also, x can be written like this: E1 E I e j minus 1, x e j plus 1 e n. You see, we need this inequality because here, for example, we are using the fact that I appears first and then j appears. Here also we are using that fact, where again et this need not be written again, but I am simply writing, and x, this however is important. It is necessary to mention here that here we are recalling the fact that x is actually also coming from nj. So this second product is again a product of elements of these n's in that order. Since these two representations of x must be unique, must be the same, we must have, okay, see, there is a possibility of confusion here. You may think that, well, these are already same. No, I mean both of them are equal to x. However, we are not saying that this as a group element is equal to this as a group element. There is nothing to say about that. That is already true. No, both of them are equal to x. However, that's not what we are saying. We are saying that these two representations must be the same, which means that you have E1 here, you have to have E1 here. That is true. But you see, what is the position of x here? X is the ith element in this product. And what is the position of x here? X is the jth element in this second product. Because the two representations need to actually be identical, so the ith element in this representation must be equal to the ith element in the second representation, which is what? Ei. So x has to actually be equal to Ei, or you can argue like this also. The jth element in the first representation must be identical to the jth element in the second representation, which gives us x equal to Ej. And that is why no matter which way you argue, you ultimately are having this x equal to Ei or Ej, both of which are nothing but E. And that's how we end up concluding that x actually needs to be equal to E. So the intersection has been proved to be trivial. We cannot have a non-identity element in the intersection, because if we have, then this uniqueness property will be violated and G no longer will be the internal direct product of those n i's. So this intersection needs to be, it must be trivial. Okay. Now we go to the second part, which takes one element A from Ni and another B from Nj. We need to prove that A and B commute with each other. Next, we have A in Ni and B in Nj. Consider the element A, B, A inverse, B inverse. We already know that such an element is called a commutator, but that's not important right now. It's just a thing that we should know. We have already come across this type of thing when we defined the commutator subgroup or the derived subgroup of a group. But what role will it play now? Let us see. Note that since A, B, A inverse belongs to Nj, why? B is in Nj and Nj is normal. That is why this conjugate of B, AB, A inverse needs to belong to Nj. So AB, A inverse belongs to Nj and B inverse of course also belongs to Nj because B belongs to Nj and Nj is a subgroup. We have, and that is why they are product, this one and B inverse must belong to Nj again. Okay, so that is one observation. Also, since B A inverse B inverse belongs to Ni because of a similar reason, and the reason is that A belongs to Ni, so A inverse needs to belong to Ni because Ni is a subgroup, but it's a normal subgroup also, and that is why this conjugate of A inverse, B A inverse B inverse also belongs to Ni. But then looking at this product of what? A and B A inverse B inverse, both of which belong to Ni, the product also needs to belong to Ni. We have AB, A inverse B inverse belongs to Ni. So this commutator has to belong to both Ni and Nj. Thus, however, we have just now proved that this intersection is trivial, and so this commutator needs to be equal to the identity element. Hence, from this it follows that AB is equal to BA, but let's see how that in turn is true. Let us see more carefully why that is the case. We can write A inverse B inverse as the inverse of BA by a previous elementary property. Hence, AB BA AB BA inverse equal to E, or AB equal to BA, and this completes the proof of this level. And now we can state and prove our main thing, isomorphism of, between the external and internal direct product. Oh, but before we prove the theorem though, there is one remark by the author. I forgot about it. Suddenly I remembered. It is that What are we seeing here? Here we are seeing that if G is the internal direct product of these normal subgroups n1, n2 up to nn, then distinct n's intersect trivially. However, the converse is not going to give us internal direct product. That is, if these are normal subgroups of some group G such that G is their product, that thing is there, and they also intersect trivially for distinct indices I and j. But that is not sufficient to conclude that G is their internal direct product. Then G is not necessarily the internal direct product of these normal subgroups. You see, we have almost everything now. The subgroups are normal, G is their product, and this condition is also true. However, all of these things still are not sufficient to give us internal direct product. And a failure of this converse we are going to see in exercises 8 and 9 of this section. Now we are going to go to the theorem. But before that, I need some ink. Once we prove this theorem, this section is going to be over. With the exercises still there, we will solve them in the community section. Do not forget that whatever exercises we are solving, I used to make solution videos, but I no longer solve exercises in video format. Instead, I post them in the community section. There are reasons for doing it, and one of them is that in a single community post I can post many solutions, but in a video, due to its length constraint, I can post only a few. That is one of the reasons. But anyway, let us now start the theorem. And once this section is over, there will be only one more, namely finite abelian groups. With that, group theory will be over. So this is 213.1, but theorem. Let G be the internal direct product of these ni's, which are of course normal. Let T be their external direct product. Then G and T are isomorphic as groups. So let's now see the proof. The proof straight away defines a function. It starts by considering a function between T and G that we are going to show that it's an onto isomorphism, and that will be the thing. Okay, so define the function psi from T into G by this rule. A general element of T will look like what? Because T after all as a set is a Cartesian product of n sets, so the general element is going to be an ordered n tuple of elements coming from these sets. So it will in general look like this, where the nth component is coming from the normal subgroup Ni. Its psi image we are defining to be just the product of these elements. The first thing you have to make sure is that this psi is well defined as a function. It's a legitimate function. That, however, is almost immediately true. Why? What do we need for psi to be well defined? We need to make sure that whenever we are choosing any input from our domain group T, the output first of all should lie in the range group G, and the second thing is that the output needs to be unique. These are the two things, two requirements for well-definedness. Now, when you choose such an input, obviously from the definition of equality in a Cartesian product, you know that these BI's are uniquely determined. If you have another set of BJ's, suppose, which are different from these BI's in some way, then the n tuple that one of them gives and the n tuple that other set gives, they cannot be equal. If two n tuples are equal, then their corresponding components need to be equal, and that is why once you have an n tuple, then these BI's are uniquely determined. That means for our given input, we have unique BI's, and so their product in G is going to give us a unique element, of course, again in G. That is why we simply write clearly psi is well defined. In most of the cases, no one will even bother even mentioning this. However, we should not forget that this issue is always there. In most of the cases, it's just trivially true, but sometimes it may cause problem. Okay, we should not be careless. So the next thing, I mean, in the text, of course, the author has gone in a sequence. First I think first he showed that this is onto. Well, ontoness we can conclude now itself. Let us do that, and then we will show other things. Let G be any element in G. Since we know that G is the internal direct product of these groups, so G is a product of such elements. That is why there exist such elements B2 in N2 and so on, Bn in Nn, such that G is their product. But then G is also the psi image of this element, this ordered n tuple, which of course is in T. Hence, psi is onto. Okay, next let us show that psi is a group homomorphism. Let what can we take? Can take anything actually. Let alpha and beta be two elements in T. Well, simply writing alpha and beta is not enough because we need to write what n-tuple they are. Where say alpha is alpha 1, alpha 2 up to alpha n and beta is this. Then alpha I and beta I belong to Ni, right? Because T is nothing but the Cartesian product of the Ni's. For such I's. Now, if I is not equal to J, okay, if I is not equal to J, then by the previous lemma that we proved, alpha I beta J is equal to beta J alpha I. We have already seen this, and it is one part of the conclusion of this lemma. Alpha J beta I similarly is equal to beta I alpha J. Now, what is going to be alpha beta T? If you calculate alpha beta in the external direct product T, capital T, then that will be this n-tuple. Alpha 1 beta 1, alpha 2 beta 2, and so on, alpha n beta n. Oh, what the hell? This is not T, this is psi. Sorry. Okay, because the definition of the binary operation in T is component wise product. That's why. Now, if you apply psi on this, that will just give us the product of these elements, that is alpha 1 beta 1, alpha 2 beta 2, and so on, alpha n beta n. However, in this product you encounter such things, beta something times alpha something else, beta I alpha j. You can flip this because of these commuting relations. You can write here alpha 2 beta 1, and there beside beta 2 you have alpha 3, that also you can flip. So after sufficient number of flips, eventually you are going to get this. If you find it a little difficult to at once see how we are eventually, of course, going to get this, you can try out a product having only a few alphas and betas, say alpha 1 beta 1, alpha 2 beta 2, alpha 3 beta 3. First you do your calculation there, you see how we ultimately end up with alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3. Then maybe take 4 things, that is 4 alpha betas, then maybe 5 alpha betas. That way you will realize why we are going to get this in the general case also. But now we are almost there. So the first part of this product within the parenthesis is nothing but the psi image of alpha, and the second part is the psi image of beta. So psi is a homomorphism. All right. So all that we are left to show is that psi is 1 to 1, because we have already shown that it's, well, of course it's well defined, then onto, and now we have shown that it's a homomorphism. So 1 to 1ness is still there. For that we consider any element in the kernel of psi. Let say gamma equal to gamma 1, gamma 2, and so on be in the kernel of psi. Then we are going to have the identity element when we apply psi on gamma. That's what we have when we have a kernel element, and on the kernel element we apply the homomorphism in question. We get the identity element. That is one thing, and the other thing is that we can of course write what we are actually going to get here from the definition of psi, which is this. Alright, now look at this equation. We can write this equation somewhat differently like this. E1, E2, etc. En equal to gamma 1, gamma 2, and so on, gamma m. Where again you understand that by Ei I mean the identity element in Ni, which actually is nothing but simply E. And since the product is direct product, that is G is the direct product of the Ni's internal direct product. So two such representations which give us a common element must be the same representation, that is identical. So since the above representations, they must represent the same element, and that same element of course is nothing but gamma psi. The above representations of gamma psi must be identical, unique. So all these must actually be equal to E. Well, you can write like this also. Gamma 1 needs to be equal to E1, gamma 2 equal to E2, and so on, and finally gamma n equal to En. But that ultimately means this. So this, that is, gamma is nothing but the identity element in capital T, the external direct product, which is identity in T. So that means that this is the only element in the kernel of psi, but then the kernel of psi is trivial, and we know that when we have a trivial kernel, the homomorphism is 1 to 1. Thus psi is 1 to 1 or injective. That is, psi is an, let me write like this, is an isomorphism of T onto G, and that's why G and T are isomorphic, and we no longer have any need to say external or internal direct product. We can simply say direct product, and that's just it. One can see one thing from this fact that T and G are isomorphic, that if G turns out to be isomorphic to the external direct product of some groups G1, G2 up to Gn, then G is also equal to the internal direct product of those subgroups G1 bar, G2 bar, and so on. Okay, so that fact we have. In the next section, which studies finite abelian groups, we are going to see that every such group is a direct product of cyclic groups, and once we have that result, the structure of finite abelian groups will be pretty much under our control fully. And this type of products or this type of facts which help us express not just groups but other algebraic structures also are very powerful. You see, whatever you are seeing here, you are going to see versions of this in the other algebraic structures also, rings, vector spaces, modules, etc. So these type of results help us. In what way do they help us? These results help us break down a complicated algebraic structure as a direct product of simpler algebraic structures, and that's why these are important. So with this, the theory part of this section is over. After this, we will turn towards the exercise problems. And let me just end the video here itself today. So that's just it. See you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.